Okay, all right. So our last speaker is Dr. Niall Gaffney. He's from the TAC Supercomputing Facility here in Austin. When we asked Niall, what would you eat if you could only eat one thing for 60 days in a row? He cheated like I did. And he said cheeseburgers because there's lots of different versions in Austin and he wouldn't get bored. So I guess tacos is cheating too, but whatever. All right, so give it up for our last speaker.
All right. Thanks, everybody. And you really do have to shout into these mics, don't you? All right. So I'm Niall Gaffney. I like to refer to myself now as sort of a recovering astronomer. I spent a lot of my career actually right here in Austin, got all my degrees at UT, and then went and worked on the Hubble Space Telescope for 13 years, building up their data archives and doing all sorts of other cool things. And then had this wild and wacky idea that I could try and teach other fields what to do with their data. But, you know, it's like any addiction, you keep coming back. And so there's a lot of good astronomy that we're doing up at TAC, and I wanted to talk a little bit about that. And also sort of refer to my nickname here. Hubblebytes, I think, is sort of, we've all heard of, you know, petabytes, and there are going to be yottabytes coming up and all sorts of other things. But to really describe the universe, we're going to need full Hubblebytes of storage. And so we're going to need massive amounts of computing power and things in the future. Let's see. All right. Advanced computing does not mean you get advanced PowerPoint. But I wanted to talk about sort of the history of what computing and astronomy is all about. And so long ago, the way that computing was done in astronomy was, well, some old white guy would go off to the telescope and observe things, and then a bunch of very, very clever women would get together and would figure things out about this. And so this is actually was the model for how things were done sort of around the turn of the century. And Annie Jump Cannon and her group over here on the left-hand side, as I'm facing, right-hand side, I guess, as you're looking at it, the right-hand side of this photo, would take these plates of exposed pictures of the sky and go through and measure how stars were moving. Annie came up with the classical way to describe different kinds of stars, the OMGF, you know, all the great different ways to classify stars. And they came up with all these things on their own. They came up with their own algorithms to do these things with their eyes and their brains, which are sort of the key things to how you discover all these pieces of astronomy. I grabbed this particular picture of them, though, because here in the background is something that gives birth to what a lot of us have been here talking about. You see sort of variable stars, which were things that they were able to pick out by eye with little magnifying glasses. In fact, one of the types of stars that they looked at are these Cepheid variables. And Cepheid variables were the first what we call standard candles. That is, that they have a constant brightness given some other measurement of them. In this case, how frequently they vary. And what that's really cool about is if you know how bright, you know, a flashlight is, say if it was 10 feet away from you, and you backed it off for a quarter of a mile, you could figure out how far away that was based on how faint that flashlight would become. It's not anything super, you know, super tough to do. It's just how light's going to go through the, going to disperse as it comes towards you. And this is a great discovery on its own that you could have these stars do this, but there was a lot of other things going on at the time. There were all these fuzzy objects up in the sky. We had no idea what they were. And this is where Edwin Hubble came along and went and measured the first Cepheids in the Andromeda galaxy and said, hey, look, this is actually an object outside of our own galaxy, and started the entire field of cosmology. And so computing has been important in astronomy and has led to the foundations of all of these great things that we've talked about. In here we've got, well, there's dark ages, which is another dark that we need to talk about in addition to dark energy and dark matter. But all of the evolution of the universe, many of these great topics that we're really sort of just starting to understand today, and they go back to that. And astronomy continued on for years and years and years under sort of that model of people go to a telescope, make some measurements, and put things together, and compute on them in sort of the human scale. And this really sort of went on and on for nearly 60, 70 years until this happened. So this is actually a photo here of the Sloan Digital Sky Survey, one of the 2 telescopes in southern New Mexico that has been operating now for about 15 years, doing great work surveying the sky. And a kind gentleman next to him who's Jim Gray, who actually came from Microsoft Research. Jim Gray wanted to do Google Earth actually in 1996. And found out that nobody gave them data because they thought that their data had value. It had oil wells and gas stations and all that sort of stuff. Well, he figured he could just turn the sphere around and prove that you could do Google Sky, and did, working with the Sloan Digital Sky Survey. And changed the way that astronomy is done in a lot of ways, because now instead of everybody just going to the telescope and getting data and taking it home with them, there's this big service with large amounts of data that you could query and put things together. And you've probably, if you've been here for several other talks, you've heard what Sloan has done and how it's changed how astronomy's done. And that's because suddenly now we have large scales data that's sitting on a large computer that people can query and run their experiments against and start to probe the universe. So why am I telling you this? Because I'm a recovering astronomer who's working in a computer center now. I'm learning biology, by the way, and there are 4 letters in biology, which makes it a lot easier than classifying stars. TCGA, it's fantastic. But I'm up at TAC, and so we are a world-class computing facility. In fact, we're one of the top computing facilities for open science around the entire globe. A lot of people don't know that we're here, but we do some amazing stuff up at TAC. And we also know that, we missed our logo. But we're proud of that as well. But we're about 180 people who are up at the Pickle Research Center campus, so that's up by the Domain where the old IBM plant used to be. And we're about 180 people there, many astronomers. I actually have 2 library scientists on staff who help with all these things. And what we do is we run big systems that don't quite look as flashy as copters that are going to be flying around Titan. They just have blinky lights and lots of them. And we run these things for people so that they can get their work done and to get their science done. And a lot of these things have to do with different, these computers are, they're not exactly the most pretty things in the world, but they're big things to be proud about here in Texas. When Stampede, this top one up here, was dedicated, it was the largest open science system in the country and the number 7 system in the world. Stampede 2, which is the bottom one down there that we had to have painted by a motorcycle shop because there were no blinky lights. Somebody needs to tell Michael Dell to stop making boring computers. This is a Dell, we bought a Dell, so we actually got a motorcycle shop to paint the Longhorns on the front of it. And it doesn't get any better. The systems start to look less and less pretty as we go along. But this is Frontera, which is a system that we brought up over the past 6 months. It's actually the number 5 system in the world. 2 of the other systems are in China, and the other 2 are with Department of Defense labs. So this is the largest at any university. And folks here have been complimenting me on some of the great modeling and simulations that they're getting done on this system already. We turned it on in July, and people thought we'd be about a year late. Just to give you a scale of this thing, there are 8,000 computers in here all that work together in symphony. Those racks are 8 feet tall. Each one of those racks contains 88 computers, and each of those computers has 56 cores. It's a massive amount of compute power here. We have 50 petabytes of storage here, along with 3 petabytes of flash storage for people that need to have really fast throughput. We do a lot of really cool stuff with this, and sort of the classics of what you do with HPC. We work with Firefly, who are at the Rocket Lab up in Leander. They've done a lot of their work with us on designing their rockets. Of course, tornadoes and hurricanes are important to the folks in Oklahoma and right now in Houston. We do a lot of simulations around that, making wind farms in West Texas better, but then also running a lot of these gravitational simulations that you heard a little bit about in the second talk, which is that is a picture of the lumps of matter that are congealing around the dark matter that we were hearing about earlier in the Renaissance simulations. And so we do these sort of standard things quite a bit. But we do a lot of other things outside of that. We don't call ourselves the Texas High Performance Computing Center. We're the Advanced Computing Center. And so we do things like work with LIGO. In fact, we work with the LIGO community. This is the experiment that was detecting gravitational waves. You heard a little bit about the 2 black holes that collided and created the gravitational waves that were detected by it. And, hence they've got another Nobel Prize coming their way. But we actually worked with them very closely to help accelerate their computing because they know physics, they don't know computers as well. And so we actually accelerated their workflows by about a factor of 4 or 5 just by helping them optimize things. And that was great because that meant that they were able to do a lot more with the computing that they had. But then after that, once they detected the gravitational wave, we actually worked with a group from Stephen Hawking's lab in Oxford. This is actually one of the last things that he was alive and working on at the time, but this was to go ahead and simulate and get everything right about those two strange black holes that were colliding and understand what's going on in these sort of conditions. This is really great because it's now gives us a much better model for what's going on with LIGO and with other gravitational wave simulations, as well as understanding precursors, and this is sort of a seed for something that's coming up in a minute, but the precursors to what you're going to detect before these things actually happen, so that maybe someday we can actually point a telescope when two black holes are about to merge or two neutron stars are about to merge. So we did a lot of really cool stuff around that, had some great visualizations. We were actually involved quite a bit in the M87 black hole, which was really cool. I have this little thing. I collect how loosely attached I am to Nobel Prizes, and this will be my third. It's a real sort of scant thing because I had I'll admit it, I had nothing to do with this other than sitting at my desk. But in this case, we ran many, many simulations of what the M87 black hole corona should look like. And so we've been doing that for many years, but then in addition to that, we worked with them on how they could do their data processing and then how they could take that really, really cool sort of image down there of what a black hole would look like if you had infinite resolution and turn it into what it actually looks like when you use a telescope with the radius of the Earth, which was what the ELT had. And so they were able to use all of this to figure out, Einstein was still right, general relativity applies at these scales, and all of those came about because of a lot of the things they were doing with us. But in addition to that, observing is changing, and I think you guys may have heard many of these different parts. That's a picture of the LSST, which is going to be renamed the Vera Rubin Survey Telescope, which I'm really, really happy about because Vera was a wonderful person and deserves something like that. But anyway, the Vera Rubin Telescope is going to be this wonderful observatory that is going to have this gigantic camera, just to sort of give you a scale of what that camera looks like. There's a picture of the moon inside of that. It has a 3.2 gigapixel camera that will take a picture every 5 minutes in multiple wave bands. It's going to create 11 trillion bits of data per hour. I mean, that's just, it's a phenomenal data rate, and you're going to have to be able to go through all of that over and over and over again because it's going to survey the entire southern night sky every 3 days. This is a groundbreaking sort of experiment. Nobody's had to do this. Nobody's been able to do this. We're going to discover so many things. But it's also something that can't be done at the scale of an observer going out and trying to reduce their data. We've got another one of these going on right here, actually, in West Texas here with the Hubblebytes Telescope Dark Energy Experiment, where they're taking it one step further, and rather than just taking pictures, they're actually going to take spectra of a large swath of the sky and go through to try and figure out what all these things are and what they're doing. In this particular case, the main focus is to look for reverberations from the Big Bang's explosion in early universe galaxies to again, pin down what this dark energy thing really is all about. But it's going to be observing millions and millions of other objects, and so a lot of great science coming out of this as well. The problem is, this sort of eye chart shows you this is what they're looking at. It's going to be a lot of noise. It's going to be a lot of fuzzy pixels. And we could try and hire everybody in the world to try and look at these things and try and classify these things, but that's just not going to work because, we don't have the money to do that. So we're going to have to turn to what's being called deep learning. Now I'm a data scientist. I can pick on the field. This is actually a gag that is stolen from Silicon Valley, the show that was on HBO or Showtime. But deep learning is really sort of this new thing that everybody thinks is a new thing, but it really isn't, because our brains have been doing a lot of this for a long time. And in this case, this was an application somebody developed to feed enough images of hot dogs and enough images of not hot dogs for it to be able to tell whether this is a hot dog or whether this is a dog in a hot dog costume. And it actually, this is the example I use every time I'm testing new deep learning algorithms. I love it. It's a passion just because it's so stupid. But what deep learning and neural networks really are is an imitation of how our brains work. And so we have all these neurons in our brains, and they get input that come in from all of our senses, from vision or whatever, and certain things will fire and certain things won't fire. And when they do, usually in a very complex deep learning network over there on the left-hand side, there may be different things that go through that trigger other things, and you get recognition that comes out the other end. We've learned how to do this with computers, is sort of the big deal. And so if you have enough data, and you can feed it into the system, this can actually be a very dumb system. You don't have to give it any information about what it's learning. You just have a lot of big computers that don't mind sitting there for days on end trying to figure out how best to program themselves to make things into a recognizable neural network. And so this is what we're going to be doing with a lot of these observations that are going to come out of these massive missions. It's also the sort of things that we'll be doing with some of the precursors that come from things like LIGOs, being able to recognize very quickly when something has happened that we may want to point every telescope in the world at. And so we're working very hard on how to make this a practical and reproducible sort of field going forward, so that we can go back to what we've done before, which is nothing's really changed. We got big telescopes, and fortunately now it's not just some white guy out there. We actually have many great women in astronomy now, and I hope that continues, and I hope we improve on that. Doing my best. My wife also is encouraging that. So we've replaced sort of the dumb white guy with these big, powerful telescopes. And these big, powerful telescopes are going to produce so much data that a room full of people stands no chance, and so you're going to need something like a Frontera to go through all of this. And once you do this, you're going to have a very similar revolution as to what we had 100 years ago, or less than 100 years ago, when we first discovered galaxies. This is going to be one of these things that changes how we understand the universe. It's going to give us all sorts of new objects, new ways that the universe works, and new ways to understand what we're looking at. And so I think that's very important, and that's one of the driving factors that we have at TAC, is to try and build this out and use this not only to understand the universe, but then to understand how we can take these applications and even try to apply them to things like Austin traffic, which has only been mentioned twice today, and we didn't talk. But this is actually another thing that we are doing right now, which is going through with some of the light pole cameras and using machine learning to identify cars and trucks and bikes and scooters. And I don't know if we can tell the difference between a lime and a bird, but we're trying. But to actually then be able to go through all those things and try and solve a very complex system that affects us on a day-to-day basis, like Austin traffic. So with that, I just want to say hi. We're here from TAC. We'll solve the easy one first.
Awesome, thank you.
And if there were a small glass of water, I might make it through questions. I'll take beer.
The best water.
That's basic.
Okay, so
Liquid
let's have
bread.
some questions. How about right down here in the front?
So we actually have 17 different clusters up at TAC right now.
So I'm just going to, repeat
I'll
the
repeat it. So
Thank you.
those look like sort of classic CPU-based clusters. Do we have any other sort of accelerators, including things like GPUs, tensor processing units? There are many other these sort of buzzword things. The answer is partially. We have pretty much all of those in-house. We do have clusters in there that are, in Frontera, there are going to be more than 3,000 GPU nodes to be able to accelerate things through CUDA and do some of the machine learning there, which will be accelerated much more by the lower precision there. We have field programmable gate array clusters that we run experimentally to understand what it is to, rather than write code to tell a processor how to process its input and output data, or rather reconfigure the processor so it just does it naturally. Which is a different way of looking at these problems, and we're looking at those. We lost our quantum person. We are interviewing new quantum people to come in and tell us about quantum computing, as that is a field moving forward, and neuromorphic. There's just all of these different forms of computation, and we want to be able to do them all because they're all going to be different tools in the case of solving Austin traffic, but. Some are going to be better at some pieces than others, and so we're not married to Intel, AMD, or anybody. We want to get the science done.
Another question. How about right here?
How do we cool our computers? All right. So the executive director of the Texas Advanced Computing Center likes to say that we are both the cause of and the solution for climate change. And that's because I can throw out some other big numbers. We are a 10 megawatt data facility. That's more than American Samoa draws. So it's a lot of power. We actually have 3 large cooling towers that we use to cool water, and we actually have then a 1 million gallon tank. So we cool water during the off hours when people aren't really running their air conditioners here in the lovely Texas summer. And so we cool water all day long except between 2 o'clock in the afternoon until about 8 o'clock at night. And we circulate that water to either cooling fans in the data center, or in the case of Frontera, we actually have cooling going directly to the chips, like many people do with their very high-end gaming PCs. In fact, the company that's doing it used to make high-end gaming PCs. So we have those forms of cooling. We also have another interesting one that I love to show off. I wish I could take everybody to the data center to go look at it because it's really cool. We have immersive cooling, where we have the computers actually put down into mineral oil, which has 10 times 100 times the heat conductivity of air and no electrical conductivity. And because of that, it's very easy to just sort of take that, run it across the processors, and then cool it off to the side with a very small, air conditioning unit, basically. So we look at all sorts of different ways to try and be less the cause of global warming and more the solution for it, as well as wind power and other things.
How about anybody up on the balcony? No. Okay. Another one right in the yellow shirt.
You said you do software optimizations for the HPC algorithms. Are those in the public domain, or are they custom algorithms?
So everything that we do at TAC is open sourced. And a lot of it is actually just helping people find the right tools and right patterns. Rewriting a for loop is not something that's an open source thing. It's just done. But we have people that understand at TAC, all the way down to the transistor level, how all the CPUs work. And they will help in some way. But then we also have people that understand, then how to build a user interface. We actually have more people at TAC who build user interfaces that understand how computer interfaces work. And that's because what we want to do is we want to make this approachable and useful to more than the few thousand people that could actually log in and run one of these things and get it out to hundreds of thousands of people. We're sort of at probably about the 30,000 user level right now, with people not even knowing that they're running with us. And we want to do that. We're doing it with HETDEX. We want to do this for a lot of the astronomical missions as well.
Awesome. Thank you. I think that's all the time we have. Let's hear it up for Niall one more time.